Thank you, Mr. Chairman. Good evening. I'm Dario Santonocito from the University of Messina, and today I show you an application of thermography to assess the fatigue performance of polymeric material, in particular polyamide 12, obtained by selective laser sintering. And I'll show you some preliminary results about the application in a quasi-static way of a uniaxial stress state. So the aim is to assess the fatigue properties of the polymeric material, but as you know, and as we have seen in this conference and in our experience, fatigue properties of additive manufactured materials have a big scatter due to the several parameters that can affect the final parts. So we need a rapid procedure to assess the fatigue properties. For traditional materials, the first application of thermography was the Risitano thermographic method. And more recently, the static thermographic method has been applied also to additive manufactured materials to derive the first damage that we introduce in the material. So the basic idea of this methodology is to just perform short tests adopting a limited number of specimens. Briefly, I'll show you the Risitano thermographic method. If we stress in a cyclic way material and we observe the temperature trend, we can see the first phase where initial temperature increment is present, as the second phase where the temperature stabilizes, until in the third phase the temperature increase up to the failure of the specimen. The higher the applied stress, the higher the stabilization temperature. However, the subtended area of the temperature versus number of cycle curve, the phi parameter, so the energy parameter that can be related to the fatigue life of the material, is almost constant. So the basic idea is that I can divide the energy parameter by the different stabilization temperature and obtain the number of cycles at which the material will fail if stressed with that stress level. Another idea that comes from a previous work of Cagliotti, where the temperature trend during a static tensile test was observed with a thermocamera, came observing the first part of the linear decrement if I put in tension the material. So moving to this assumption, Risitano proposed the static thermographic method to assess the first damage that I can introduce in the material if I stress it. So during a static tensile test, I have a first phase of the temperature where there is a linear decrement of the temperature signal that follow the Lord Kelvin's law. This is the thermoelastic law, followed by a second phase where there is a change in the slope of the trend of the temperature, and then a third phase that is corresponding to the yielding stress of the material, where and after of this point the plastic deformation are so high that the temperature rise up to the material failure. So if I'm able to assess with my infrared camera the change between phase 1 and phase 2 in the temperature signal, I can relate it to a limit stress So this limit stress can be thought as the first microplastic damage that I'm introducing in the material. So whenever I stress my material in a cyclic way, it will reach failure. There are a lot of papers regarding the application of the static thermographic method. Now are more than 10 years of research. And we are also developing some machine learning approach to detect the correlation between the temperature point and to automatically assess the limit stress. But the application that I'll present you today is regards the polyamide 12 obtained by selective laser sintering. We created some specimen according to the ISO standard, and the specimen are produced with an orientation angle of 0 degree respect to the x-axis of the building plane. Regarding the experimental setup, we have a servo-hydraulic testing machine of 25 kilonewton maximum capacity and an infrared camera, FLIR A40. We perform 3 kinds of tests. A first test that is a classical static tensile test on 3 specimens with a crossed speed of 5 millimeters per minute, followed by a stepwise fatigue test where we applied the Risitano thermographic method to assess the fatigue limit of the material, performed on 3 specimens and choosing the delta of the stress level between 1 and 2 megapascal and the delta of number of cycles of 3,000 cycles. The stress ratio was 0.1 and the testing frequency was 1 Hertz, just to prevent excessive heating of the material. And finally, we perform a series of quasi-static tensile tests on 2 specimens with the same parameters of the first series of static tensile tests. We perform 10 cycles for each specimen up to the failure of the specimen. So regarding the static tensile test, I show you here the stress strain curve of the materials. Here I report the value of the Young modulus, the ultimate tensile strength, and the deformation at failure of the specimen. And here I also report some other value from the datasheet of the material and other literature research present. And the data is quite in agreement with the literature. But now, observing the temperature trend, here is the same curve, stress curve that you has previously seen. And here we have the temperature signal filtered with an RLOS filter. And here we can detect the first linear phase of where the temperature decrement, followed by the second phase. We can make the linear regression of the 2 sets of data, the blue circle and the blue square, make their intersection, and then we can find a value of the limit stress of 25.4 megapascal. The same is valid for the other test. Here we have also the first linear phase, followed by the second phase, and here is the third phase that it is not important for our population, so I don't report it. So on average, we have a limit stress of 24.4 megapascal. So in order to validate this value, we move to stepwise fatigue test. We increment the stress level of the applied stress level. Here you can say the variation in the temperature signal respect the number of cycles. And we record the stabilization temperature for each stress level. We can plot the stabilization temperature versus the stress level. And as we can see, we have a bilinear trend. So we can make the linear regression of these two sets of data and assess the fatigue limits of the materials as 25.4 megapascal. So it is in good agreement with the value obtained with the static thermographic method. Moving forward, we perform a series of repeated quasi-static tensile tests. Here I report the first cycle where we have the loading curve that is stopped and then unloaded the specimen till 0. And here we can see also the first linear phase and the second decrement phase of the temperature, and we can assess the limit stress as 21 megapascal. Moving to the other cycle, I just report the second cycle and the fifth cycle. Here we have the same stress curve, but here the temperature signal is not very clear, so it is not possible to assess in a clear way the change between phase 1 and phase 2. At the end, in the 10th cycle, we lead the specimen up to the failure. So we reload the specimen and then the specimen break. We can assess a change in the slope for approximately a stress level of 29.5 megapascal. So in conclusion, what we have seen is that the results given by the static thermographic method are in good agreement with the Risitano thermographic method. I want to point out that to verify the obtained value of the stress of the fatigue limit that we have found, we have to perform a classical fatigue test campaign. On the other hand, this kind of campaign consume a lot of time to be performed, and also we need a lot of specimen to be tested. I want also to point out that for the static thermographic method, the test time is about 5 minutes, is a simple static tensile test, and we just adopt free specimen. The same apply to the Risitano thermographic method. The further development of the work is just to analyze how the damage progress within the materials, both in a static way, like this, the one that I present now, and also in the fatigue regime. So thank you for your kind attention. I'm open to any question.
Thank you, Dario, for the presentation. Is there any question for the audience? No? I have just a curiosity or comment. Do you plan also to investigate the effect of the strain rate on the determination of the fatigue limit with the static thermographic methods? So I see that you carried out the static test and across at the speed at 5 millimeter per minute. Okay.
It depends.
Limit for the thermographic measurements, or
so the basic idea of the static thermographic method is to make the the test in an adiabatic test condition. So at the moment, we are finding the correct stress or strain rate to clearly see the phenomena, okay? But if you have low velocity or high velocity, the phenomena is present, okay? But for our observation capacity, we have to set the correct stress rate or strain rate. And we here the curve are just the stress one, but in other kind of tests, we want also to put the DIC just to observe the evolution also of the strain and see if there is also a clear evidence of this phenomena in the strain range of data.